finals exam time. Your final exam is due Monday, December 13th. Yeah, I don't know. I looked at the exam schedule, and that's what it said. So, yeah. And that is, 10 a.m. I will open the exam by December 1st, which should be the end of this week. If I don't do that, please email me. But, yeah, we got a lot of time for studying or something or whatever. Anyways, she'll have 2 sections, HackerRank and Blackboard, just like before. It's going to function just like before. HackerRank's time, you'll be allowed to log in if you lose connection. Blackboard will be timed, but will not allow you to log in. Therefore, when you take the exam online, make sure you save your work to a separate document. If when Blackboard crashes, email me your document ASAP. I am not reopening this exam, so once it opens, please Control-A, Control-C, Control-V. All right? So, final exam will consist of programming problems that you must solve and stepping through iterations of algorithms showing the state of each step. Big O will be a significant topic during your final, and we're going to go through that momentarily. Since HackerRank has an auto-completion and testing section, please utilize these features to ensure your code's correct. HackerRank grade is based on the percentage of test cases correct. All right, what are our topics? Array, linked list, vector, stacks, queues, sets, maps, trees. We have binary search trees, heaps, priority queues, and B trees. We have hash tables, both chaining and linear probing. We have heaps, and then we have graphs with the adjacency list and adjacency matrix, and you will see probably Dijkstra's algorithm, although possibly Prim's. Some algorithms that we went through: sorting, bubble insertion, selection, quick, merge, and heap. Searching, we went through linear, binary, depth first search, and breadth first search. Depth first and breadth first are very important, especially breadth first. Traversing, you're in a big binary tree, you got pre-order, in-order, and post-order. That was just on the CSU final exam. So there it is again. Graphs, simple, meaning no loops, strongly connected. I'm not going to ask too much on those, but you will want to look up depth first and breadth first, as well as shortest path, aka Dijkstra's. Make sure you understand how you delete and insert in each data structure, as well as searching, and then copy constructor. Okay, what do you need to know? Comparing and contrast with space complexity and runtime complexity and big O notation. And again, here's where I'm sorry, all the people online, your battery be sad.
And all the people who are going to review this video later.
All the people who wish to review this later, sorry about this. Look at that. All right. What were our data structures? They're array. What type of array? I already misspelled it. All right, we'll do the unsorted. And then we have the sorted array. What was the next one?
The linked list.
Linked list. We also had the unsorted, as well as the sorted. I really hope I don't run out of space. What was next? Which binary tree?
Search tree.
Yeah, the binary search tree.
Heap.
And we had the heap, that was the other binary tree.
B tree.
We had the B tree.
Hash table.
Hash tables, yep. Queue. Yes, we had stacks and queues, but we're going to say those were implemented with one of these things, so let's not do that yet. What else do we have on here? Should just be the graphs, yeah. So we'll have the adjacency matrix graph. Oh boy. the adjacency list graph. Oh good, I didn't run out of space. Oh hey, we had quadries today.
Beautiful.
So what do we do with these things?
Search, insert,
Okay.
remove, contains.
Okay, so let's start with, well, we want to add something to it, so we add. We'll just have generic or insert. We'll do generic insert. We'll start there. I'll call it generic just to make sure it's,
Generic enough.
yeah. We just want to add a number to it. Just want to add something to an unsorted array. What's the big O?
Just one.
For best and average, it's O of 1. What happens in the worst case?
O of n.
O of n. Why is that? O of
So you
n?
have to recreate it,
Yeah,
copy
right.
it all over.
Yep. That's gonna be bad. All right. What happens? What about a sorted array?
Same story.
Not
Wait, no,
sorted.
it's over at O of n.
It's O of n. How about an unsorted linked list? Always O of what? You just create the node, shove it in there. In the beginning or the end, we don't care. How about a sorted linked list? And why is it O of n?
Because you have to check all the values.
Yeah. And searching, even a sorted linked list is still O of n. You have to do a linear search. Binary search tree.
Should be the log of n.
Yeah, we're going to go ahead and do best and average is log of n. Worst is O of n. I forgot to put my big O right there. Oh well. How about a heap?
Best and average is log of n.
Right. Best average is log of n. This one can have a worst case of O of n, but it's pretty rare. How about a B tree?
How many child nodes?
There are M child nodes.
Okay. Guess best and average is log of n.
Yeah, this one's always going to be log base M of n. All right. How about a hash table? I thought I heard it. For best and average will be O of 1. What's the worst case? O of n. So I didn't, excuse me, I didn't divide this out into open addressing or chaining, but in open addressing, if you end up having to search the whole hash table to find it, it could be O of n. That's not good. How about to insert something in a adjacency matrix graph?
Just O of 1.
O of 1.
O of n.
O of 1. Because it's a matrix, you just shove it right there.
Oh yeah, we don't have to.
How about a adjacency list? Well, you jump to the list, and then you just add it to, you jump to the spot, that's O of 1, then you're adding to an unsorted linked list, which is O of 1. O of 1 plus O of 1 is O of 2.
Spicy.
I want to write O of 2 so badly. All right, quad tree.
Log of base m of n.
All right, so I didn't talk about this too much. but it's log base 4 of n, and worst could still be O of n, because if it somehow does that chaining where everything's going like the upper right or the lower left, then it has the same problem as a binary tree. That just happens really rarely, but it can. All right, so which one's winning?
It depends.
What are you talking about?
Oh, yeah.
The JC matrix and the JC list are O of 1, as well as the unsorted linked list. The rest of these are terrible. Right? Mm-hmm. Sure. Okay.
Sure. Let's move on.
All right. We're gonna do two more. We're gonna do add front and add back. I should have given myself more room. Oh well. Anyways, unsorted array. Adding to the front is what? O of a front.
O and
It's always O of it. What about adding to the back? Ooh, unless you got, yeah. Best and average is O of 1. Worst case is O of n. All right, how about the sorted array? That makes no sense. Right? You don't add to the front of a sorted array. Yeah, so I sometimes put question mark. I actually prefer this. Right? Don't be doing that. You're using the wrong data structure. So like infinite or whatever you want to write. You know, not happening. Can't do it. All right, unsorted linked list. Adding to the front is O of 1. Adding to the back is O of 1. Wow, that linked list is doing great. How about sorted linked list? Unhappy. Binary search tree? Unhappy. Heap? Unhappy. B tree? There's a reason I did this. Unhappy. Hash table? Well, that's super unhappy. Graph? Okay, these are all just unhappies. All right. I write that in. Wow, that was it? Okay. Sometimes you do want to add to the front, you do want to add to the back of something. But a lot of times you're doing generic insert. It really depends on your data structure. All right, here we go. Let's see. Oh, search. Or contains. You want to call it search or contains?
search.
Search. All right, searching an unsorted linked list.
Oh, we went straight to linked list.
Unsorted array.
O of n.
O of n. How about a sorted array?
Log of n.
Log of n. Well, you know what? The unsorted linked list was just killing it, but go ahead. O of n. It was looking so good. Sorted linked list.
Still O of n.
O of n. Binary search tree.
Log of n.
For best and average, it is log of n. Otherwise, for worst case, I did it again. It's O of 1. I mean, O of n, sorry.
It's like worst case is faster than best case? Holy cow.
Yeah! All right, heap. You can't search a heap. You shouldn't, so I'm going to put like unhappy face /
Happy face.
How long does it take to search the heap?
O of n.
Oh, then, because you're searching the entire array. You really shouldn't be doing that. But you know what? Whatever.
You do you.
You do you. All right, B tree.
Log of base m of n.
Yep. Log base m of n. Hash table. Ooh. Hmm?
O of 1.
O of 1, yep. Worst case.
Of n.
Spoiler alert, that's not going to get old anytime soon. The JC matrix. Want to find
O
the
of
point.
1. The best and average is O of 1.
It's all O of 1. The JC list. All right, we're going to call it O of M, where M equals length of list. Linked list, right? Because you got to search the linked list. So it could, M is probably substantially smaller than N, but it is based on something else that we don't have enough information to put right there. Hey, quad tree.
Log base 4 event.
Yep, it's not going to get old anytime soon. Worst case, O of N. All right. So we're going to do get largest.
Ooh, keeps excited.
What's that?
Keeps excited.
It really is. I got this, I got this, I got this. All right. Unsorted array. Although the heap is not actually that excited, but yeah, unsorted array.
Okay.
Largest.
Yeah, O of N, you gotta look the whole thing. How about a sorted array?
O of 1.
O of 1. Nice.
Wonderful.
Killing it. Yeah.
Just that one thing.
Look, man. Actually, the log of N on searching is pretty
Yeah,
good.
that's pretty good.
That's what is
But
it,
that
D3?
add though.
Look, we all got our problems, all right? All right, unsorted linked list. Oh, man. All right, sorted linked list. You could keep a pointer to the tail, right? So we'll call it O of 1. Ooh, it's killing it too. Oh, too bad it's got some O of N's. How about the binary search tree?
Open.
Well, best and average, you just have to go along the right or the left, right? And that's going to be log of N. Unless, of course, that's the way the binary search tree decides to just sprawl out, then it's O of N. Oh, man. All right, the heap. What?
1.
Yeah, we'll call it O of 1, unless you're, no, we're not removing, we're just getting the largest. B tree. I'm going to just write it in, because I'm tired of it. Heap.
Tired of B tree being the same thing.
Yep, all right, heap. We're going to again do an unhappy face, because you really should, I'm sorry, hash table, sorry. Because you shouldn't be looking for the largest of a hash table, that doesn't make much sense. But if you were going to do that, you would
Open.
O of N. And some languages do allow you to do that. Largest of the JC matrix.
N squared.
You got it. Woo! Oh,
Or
bad.
N squared.
Yeah, you didn't think they could make it worse than N, could you? Well, we did it. All right, how about the adjacency list?
Would it just be O N M?
Yeah, N times M, where M is the length of those number of edges you have in the list. M could be N, or it could be 1 or 0, or not 0, but pretty low. Quad tree. Okay, thank you. All right. Whew. Wow, that looks ugly. Can y'all even read that from back there?
Nope.
Nope. No. Great.
I'm gonna try and take a picture of it before he erases it.
Yeah. Put it up on Discord. See how accurate it is.
Absolutely.
Ah.
I might even put it on ACM.
All right, we're gonna do generic remove. Are we removing? Removing some random value. You can think of it as random remove. Might be a better word for it. Let's actually like that better. Something randomly in the unsorted list. Well,
Then
Yeah, you gotta find it, and then you gotta shift everything over. Sorted. Well, it takes log of n to find it.
O then.
Why is it O of n?
So you still have to move everything else down.
How about an unsorted linked list?
O1.
Oh, you gotta find it.
Ugh. O.
Yeah. You know, it was doing so well, and then blah. How about a sorted linked list?
Log of n. No. O then.
Yeah, it's O of n because you gotta find it. Binary search tree. Again, it's not getting old. Well, you got to find it and then remove it, and yeah. Heap. You don't do that. Don't do that. B tree. Sorry, I heard y'all say it, but no one said it. I know someone did say it, right? Log-based M of n. Hash table. Loud and proud. Someone said it. Does anyone?
O of n.
To remove, you gotta find it.
Doesn't that? Yeah, it takes O of n to find it, right? Uh-oh.
O of 1. Worst case, O of n. All right. Let's see. Random remove on a Jinxie matrix.
O1.
Man, you know, this thing's doing great if you just don't need to get the largest. Or add and remove from the back. All right, a JC list. What are we doing? We're removing. So that'd be O of n. Because you have to remove from the unsorted
Yeah.
link list, which is O of n, based on n. There we go. All right, quad tree.
Log of 4.
Log base 4 of n. Oh, all right. Let's well, we had add front and add back. Let's do remove front and remove back.
Okay.
I mean, that's what we used for our stacks and queues, right? So this is a very popular operation, which of course is going to have a lot of unhappy faces. All right, let me come from this angle now. Unsorted array, we want to remove the first.
Open.
Oh man, we're going to remove the back.
O1.
Oh boy, all right. Sorted, we don't do that. Unsorted linked list.
O1.
Oh, one? How about the other one?
Oh, we have pointer at O1.
Yeah, it's O1. Great. Sorted, we don't do that. Binary search tree. What is the front? Heap, again, what's the front? Well, wait a minute. Do we want to call remove front the same as remove largest? That's a good question. Because in the heap, it does have the front. It just doesn't have anything else. So we're going to go, I'm going to actually call it O of log of n / unhappy face. There we go. Because you do remove the front. Remove front. Well, let's do this. Well, if I do remove largest, yeah, we're going to do remove largest separate because that's actually, because the other ones will actually have an answer to that. So we'll just go unhappy face. I think these are unhappy faces all the way down. All right. Now let's do remove largest. When was remove largest really useful? A priority key. All right, unsorted array.
O then.
Yep. Sorted array. Remove the largest.
O1.
O of 1, yeah. Unsorted linked list.
O then.
Sorted linked list.
O then. Wait.
O1. It's the tail pointer or whatever.
Yes, O of 1. Binary search tree. You have to log in, you gotta find it, then get rid of it. Worst case could be O of N. Remove from the heap. Now he's happy. B tree. Log base him in, you gotta find it and get rid of it. Hash table.
Honestly, this thing right here is showing me why people would pay money for a B tree.
Yep. Oh yeah, look at that. It either does it, or it either doesn't do it, or you get log of n base in. Yeah, that's not going away anytime soon. All right, and GC matrix. Remove the log. Did we talk about remove? We're talking about edges. Yeah, I'm talking about edges. We didn't even talk about nodes. We'll just assume edges, because if we were to do nodes, that would be weird. I mean, not weird, but annoying. So if we want to remove the largest edge from the GC matrix,
O then squared.
we gotta find it. GC list. N times M. And the quad tree, we want to remove the largest, so we just shove up to the, actually down low. So that would be best and average would be log of base 4 of n. Worst case, in case it's always going down there, is O of n. Great. Whew. Okay. Oh man. So we got insert, we got search, we got get the largest, we got remove the front, remove the largest. What else did we do a lot of?
Subscript operator? Or like
Oh yeah, subscript. No, that's a great one. Think of this as get the nth element. Unsorted array.
1.
1. This is the biggest advantage of the array, by far. And it's why it's used so much, is that getting just any random value, if you know the index, is 1. Sorted array, this makes no sense. Unsorted linked list. We did it.
Oh, then.
Oh, then. Sorted linked list. Well, hold on.
I mean, it still makes sense.
It makes sense. We'll go ahead and give it O of 1. It makes sense.
You
It does
could
make
do it.
sense, you're right. It makes sense, but we can do it on a binary search tree. It's really annoying. Well, you've done the traversal, right? You just do an in-order traversal until you hit visit the nth time, and then you get it. It's O of n because you have to go through it one by one. How about a heap? This is where things get tricky, because the heap is a binary tree, so theoretically this makes no sense or is O of n. But since it's an array, yeah, it could be O of 1 because you can, since you can calculate, since the tree is laid out a certain way and you want to apply some ordering to it, you could calculate the exact spot. It would take some multiplications, divisions, and whatnot. And you could
It'd
find
be a
it.
really bad O of 1.
Yeah, it's a really bad O of 1. It's a O of unhappy times 1, yeah. Right, but it is O of 1. A B tree, oh boy. I'm just going to, for the sake of argument, because at some point you're like, don't do this, right? Just don't do it. Hash table. We're going to do the same thing because you'd have to go in. Well, there's no ordering. This implies an ordering of some sort. The hash table doesn't really have an ordering to it. That's the point. How about a graph, a JC matrix? Oh, that one's tricky.
Wait.
We'll do the slash thing. It's either whoa.
We can't have that.
Can't
no
we have
smiling
that
faces
searches?
around here.
We'll call it O of N, or O of 1, sorry. We'll do GNC list. We'll either say unhappy face or O of M. Quad tree. It's the same thing as a binary tree because you have to walk it just like before. Oh boy. Okay. Anything else we did?
Let's see. Sort.
Sort.
The most vague thing ever.
Sort. I don't think sort makes too much sense in this context because if it's already sort, yeah, we're not going to do that one. Merge. Let's do merge. The reason I'm doing merge, because the sorted linked list is not doing too well. We want to merge two unsorted arrays into one sorted array.
Oh, one sorted array?
Yes. So
Get it.
it's either O of n squared or O of n log n. Because if you sort the two arrays and then you merge them one by one, then you can do n log n, otherwise it's n squared. That might be a little confusing at first. Let's move on. Let's go over here. Merging two sorted arrays. What's the big O for that one?
O of n log n.
No, it's just O of n. Because you just walk the total number into the new array. There's no extra logging. Maybe it'll make a little more sense with, unsorted linked list. I'm going to go ahead and call it O of n squared. How about a sorted linked list? Maybe this makes a little more sense. What's the big O to merge a sorted linked list? Two linked lists, they're sorted, so you only have to look at the front two, and you're looking at them one by one. The final linked list has n elements. How many compares did you have to do? Bless you. Where's the log coming from?
Because you are separating each individual list.
I think we have merge sort stuck in our heads right now.
It's not the merge sort, it's just the merge. That one merge step. What's the big O of the merge step? Yeah, it's O of n. Because you just take, which ones of these? Remember, the two in front are always the least, correct? So we just take which one's next that's the least. So you're always comparing the front two until you're done, and then you move the rest into there. So it's O of n because you're only looking at n elements. In merge sort, you do this O of n operation log of n times, is why you're thinking merge sort. So yeah, it's O of, where am I? O of n. How about merging a binary search tree? Take two binary search trees, put them and make a mega search tree. We'll call it O of n, just for the sake of argument. Actually, a lot of these are going to be O of n, which is fine. Heap, you're merging two heaps. Ooh.
Wouldn't you just insert?
Yes, but you'd have to do it n times, and each insert is, oh, actually, I'm doing this wrong. Let me back up. Back up to binary search tree. So you'd have to insert. Well, how big is insert? Log of n. How many times are you inserting? N times. So what's the merge for binary search tree?
N log n
There we
or
go.
n squared.
Right, so best and average will be n times log n. And worst, and I'm going to get rid of my big O's because I'm running out of room, n squared. Okay, how about a heap?
N log n
Yeah, we're gonna just call it n log n for the sake of argument.
or n squared.
B tree.
And log n.
It'd be n times log base m of n. Because every time you insert, it's base m. So it is faster than these other ones. Hash tables.
Oh.
Best and average, O of n, because you're doing O of 1 n times, but worst case,
Times square.
yeah. You see how this is starting to be based on these previous ones? Very helpful. What's the next one? The JNC matrix. We want to add n times. So we're going to merge all the edges together. All right, yeah, so that's O of n. That makes sense. Because you have a bunch of edges, you're merging them into one matrix. Okay, cool. The JNC list. Same thing. Because when you merge the edges, you're just adding it to the linked list, which we know is O1. And then the quad tree, it's again that. All right, guys. Don't fail me.